Hi, Dr. Kiran here. Welcome to another video of General Chemistry series. Today we will discuss the development of atomic model with a brief overview of atomic history. Atom has laid the foundation for the most of the branches of science, and most of the scientific principles are based on the structure and properties of these atoms. So it's really interesting to learn about the history of atomic model development and how the scientists arrived to the current form of atom. Evolution of the atomic theory or model started from 400 BC when the Democritus proposed that matter consists of invisible and indivisible solid spheres called atoms. For example, milk is composed of milky atoms, and solids are made of solid like atoms. However, it was a time when no scientific experimental evidences or theoretical concepts were developed. So, in the limited knowledge of that time, it laid the foundation of atomic research, or it created a curiosity about the building blocks of matter, and philosophers of those days started thinking about the matter and its structure and composition. By the end of the 18th century, science provided the strong evidences of the existence of atoms and developed the theories on the conservation of mass and the law of constant composition. In 1789, Lavoisier gave the law of conservation of mass. According to him, atoms in a matter can never be created nor be destroyed, but they can be moved around and can be changed into different kind of particles. For example, if we heat the 2 grams of compound A and it converts into products C and D, the total mass of two products formed will be equal to the mass of the reactant A in this chemical reaction. In the year 1794, the French chemist Joseph Proust formulated the law of constant composition and proportions from his work on sulfides, metallic oxides, and sulfates. He stated that elements are present in a particular composition. For example, no matter how many water molecules are there, all of them have constant composition of 2 hydrogen and 1 oxygen atom. He also proposed that masses of elements in a compound always occur in the same proportions. For example, carbon and oxygen in carbon monoxide are always in 1:1 ratio. And in carbon dioxide, they are always in 1:2 ratio, and 1:3 ratio is present in carbonates, and so on. These two laws became the foundation of Dalton's theory of atom. James Dalton was an English chemist and physicist, and he extended Proust's work and converted the atomic philosophy of the Greeks into the scientific theory between 1803 and 1808, and he provided the foundation of atomic chemistry. He proposed that atom is the smallest particle of an element. They are the hard spheres and cannot be divided by any chemical means. An element has similar kind of atoms. For example, gold will have only gold atoms. Atoms combine in different forms, compositions, and proportions to make compounds. He gave the concept of elements and compounds, and he differentiated the matter into elements and compounds. His theory couldn't explain many phenomena and properties of atoms. However, this theory supported and initiated the further research on this topic, and he became the first one on the timeline of atomic model development. Until 1897, atom was indivisible particle. Then in 1897, J.J. Thomson discovered the electrons, or negative charged particles, in an atom using cathode ray tube, where he found that on heating the metal filament by high voltage source, it emits the cathode rays, and these rays make a glow on fluorescent material. On applying external electric field, these rays were deflected towards the anode, or positively charged plates. So they must be negatively charged. On the basis of this, he gave another theory of atom. According to him, atoms are solid, positively charged spheres. Electrons are negatively charged and are stuck inside the positively charged atom. After his discovery, atomic model became the two-particle system in which atom can be further divided into positive and negative charged particles, the electrons. Thomson's atomic structure described atoms as electrically neutral. That means the positive and negative charges were of equal magnitude. His model was also called plum pudding model. It was almost 80 years to evolve the atomic theory from single particle to two particle system. Rutherford, a student of J.J. Thomson, modified the atomic structure with the discovery of another particle called protons. His atomic model was based on the positively charged alpha ray scattering experiment. He bombarded a thin gold foil with the alpha particles and noticed that most of the rays just went through the gold foil, and only a few rays got reflected back at an angle of 180 degrees after hitting the gold foil. On the basis of this experiment, he concluded that since most of the alpha rays have passed through the foil, most of the space inside the atom must be empty. Few rays that have been deflected must be because of repulsion with some other very strong positive charge inside the atom, and he called that nucleus. He proposed an atomic model that postulates atom's positive charge resides into the nucleus, and size of the nucleus is very small as compared to the whole atom. Remaining empty space is occupied by electrons, and number of positive and negative charges is equal in an atom, so atom is neutral. Electrons circulate around the nucleus much like planets revolving around the sun. This planetary model of an atom comes in 1909 on the timeline of atom. The first one is that if atom has planetary structure, electron is not like planet. It's a charged particle, and being the moving charged particle, it should continuously emit energy. And because they are continuously emitting energy, they should give a continuous spectrum, but it actually gives a line spectrum. And as per classical theory, if electrons are continuously emitting the energy, they should ultimately fall into the nucleus. Let's see how it happens. If the electron keeps radiating the energy, then he must follow this path, and it keeps getting closer and closer to the nucleus and ultimately collapses into the nucleus. In the 1915, Niels Bohr described the atomic structure of an element in the light of Planck's theory of quantization. He proposed that electrons are restricted to stationary orbits around the nucleus, and electrons revolve around the nucleus in these stationary orbits only. And each orbit has some quantum number, and that's why the energy of the stationary orbits is quantized. As long as the electron stays in its own stationary orbit, there will be no absorption or emission of energy. Electrons can jump to higher levels by absorbing energies that can be given by Planck's equation. When the electron moves to lower energy level, it loses or emits its energy. Although Bohr's atomic model explained a lot about atom, but it was only applicable to small atoms like hydrogen atom. Emission spectrum showed that each line spectrum was seen to be a combination of a number of smaller discrete lines. His theory couldn't explain some other phenomena as well. In 1923, Victor de Broglie, a French physicist, proposed that just like other matter and radiations, electrons also have dual nature, and they can act as a particle or a wave. De Broglie wavelength and momentum of the particle can be given by the Planck's equation. However, it was based on inspiration from the Einstein's theory that radiations can have both particle and wave-like properties, and it lacked the strong mathematical evidence at that time. Heisenberg then gave the principle of uncertainty in the measurement of energy and momentum of electron. He postulated that energy and momentum of the small particle like electrons cannot be accurately measured simultaneously. Let's understand it in detail. For the big objects or macro world, we can get to know the position and velocity of a moving object accurately. However, in a quantum world where charged particles with a mass as low as the mass of electron, it will not be possible to know the position and measure the velocity or momentum of the particles simultaneously. Even if we try to slow down the speed of electrons, usually in these practices, we illuminate these particles with powerful light. So when the light hits the electron, it will change its position or it will change the velocity. So if we try to know the position and its momentum, uncertainty will be very high in the measurement. A powerful model of the atom was developed by Erwin Schrödinger in 1926. Schrödinger combined the equation of wave behavior with the de Broglie equation to generate a mathematical model for the distribution of electrons in an atom. In his atomic model, Schrödinger assumed that electrons act like standing waves, and they are in constant motion and don't have any fixed position. so they make an electronic cloud. And he stated that electrons are present on the probable areas called orbitals in the electronic clouds. According to the quantum atomic model, an atom can have many possible number of orbitals. The orbital wave function is a mathematical function used for expressing the coordinates of an electron. And the square of the orbital wave function is called the probability of finding an electron or its orbital. In the Schrödinger's model, it requires three coordinates or three quantum numbers to describe the orbital in which the electrons can be found. These orbitals can be categorized on the basis of their size, shape, or orientation. An s orbital is spherical with the nucleus at its center. A p orbital is a dumbbell shaped and can have three different orientations in the space. On the basis of their orientation in the space, they are categorized as px, py, and pz orbitals. Probability of finding an electron is higher in the lobes and least in the nodes of the orbital. Same is true for the d orbital. It can also have different allowed orientations in the space and have 5 different types of orbitals, and probability of finding an electron is higher in the lobes and least in the nodes. These are different orientations of f orbitals. This model explains the spectral emission lines of atom and ions, the modification of energy levels in the presence of electric or magnetic field, and because this model is based on the orbitals, it also explains the chemical bonding and stability of the molecules to a certain extent. The last two models of Niels Bohr and Erwin Schrödinger are the most used and accurate models considered until this time. Thanks for watching this video, and please like, share and subscribe.